Good morning, and thank you for your interest in our research. In the following hour, we will present how to attack an NTP server with fake timing signals. During this presentation, we will discuss the NTP server, its stratum model, the reference clock, how to forge fake timing signals, and how to attack an NTP server. Normally, we can set an NTP server for our computer to synchronize time automatically. Sometimes, our mobile phones also get its time from an NTP server. This type NTP server is associated with our daily lives. NTP servers are also widely used in private networks, such as power grids and railways. For example, power grids have to synchronize their automatic equipment in less than 10 milliseconds. As we know, our computer or phone can get its time from an NTP server. But how does the NTP server get its time? Well, according to the NTP protocol, stratum levels define the distance from the computer to the reference clock. A reference clock is a stratum 0 device that is accurate and has little or no delay associated with it. Stratum 0 device cannot be used on the network. Instead, they are directly connected to a stratum 1 NTP server. A stratum 1 NTP server acts as a primary time server. It gets its time from a reference clock, namely stratum 0 device. A stratum 2 server is connected to a stratum 1 server over a network path. Thus, a stratum 2 server gets its time by sending NTP packet requests from a stratum 2 server. And so a stratum 3 server gets its time from a stratum 2 server, and so on. So the original time source is the reference clock. In this presentation, we will discuss the reference clock and the stratum 1 NTP server. Well, as this picture shows, a large amount of NTP servers are deployed with the open source NTP version 4 software. From the newest NTP version 4 source code, we know that NTP version 4 supports almost 4,000 types of reference clock. The most commonly used are the WWVB, DCF77, GGY, MSF, and GPS. But why does the stratum 1 NTP server use the radio clock and the GPS as its reference clock. In fact, there are three classes of accurate clock: the atomic clock, GPS, and the radio clock. The atomic clock is very accurate but expensive. The GPS satellite has a built-in atomic clock and broadcasts the time of this atomic clock in its navigation data frame. The timing signal of reference clock is also controlled by an atomic clock. So with the broadcast of these wireless timing signals, we can use a low-cost receiver to get almost the same accurate time as atomic clock. The radio clock and the GPS have been widely used to build street-mount NTP server. Well, on the NTP website, there's a list for its supported radio clock and the GPS receiver cards. We can connect a receiver card to a computer to build a street-mount NTP server very easily. And there are also a large amount of integrated street-mount NTP servers that can be selected for industrial use. Take this product as an example. From its product description, we know that it supports DCF77, MSF, WWB, and GPS as its reference clock. Now let's talk about how to forge these timing signals. Our aim is to DIY a uniform circuit to transmit all of these radio clock signals. First, let me introduce the signal features. The WWB timing radio station is operated by the USA according to its encoding mechanism. It uses different passwords to represent different binary data bits. As this chart shows, if its amplitude is reduced for 800 milliseconds and then increased by 200 milliseconds, this is a non-data special bit, which we call as marker. If its amplitude is reduced for 500 milliseconds, then increased by 500 milliseconds, this is a data bit with the value 1. If its amplitude is reduced for 200 milliseconds, then increased by 800 milliseconds, this is a data bit with the value 0. And the WWB timing signal uses a 60 kHz carrier. After adding the signal to the carrier with the amplitude shift keying modulation, if the input signal is at low level, it transmits with reduced amplitude. And when the input signal reaches high, it transmits with for amplitude. The output of these signals represents the binary data bits marker 1, 0, and 1. It sends one frame at the start of each minute. Each frame consists of 60 bits. If it transmits 1 bit per second, the frame starts with a marker bit and almost sends a marker bit every 10 seconds. To reduce error, each frame contains the minutes, hour, year, day of year, and the day of week. The final bit also is a marker. So if the receiver gets 2 sequential marker bits, it means that a new frame is prepared to be received. Well, the GGY radio station is operated by the Zheng. Its encoding mechanism is very similar to the WWB. The difference between them are the different path widths of each bit and the different frame encoding. It also uses the 60 kHz carrier. The DCF-77 is operated by Germany. In fact, it's also similar as WWB, except it uses the 77.5 kHz carrier. As we mentioned before, the carrier of GGY, WWB, and the MSF are 60 kHz, while the DCF-77 is 7.5 kHz. We want to design a uniform circuit. It's capable of transmitting all the above radio clock signals. So we use the DDS module to generate carrier. This DDS module can generate a 0 to 40 MHz wave. And Arduino, there's an open source driver. It makes the whole thing a little easier. The formula is very simple. Take the GGY as an example. When sending marker bit, it requires sending the carrier 0.2 seconds of for amplitude, followed by 0.8 seconds reduced amplitude. In this case, when it requires you to reduce amplitude, just shut down the DDS module. When sending the bit 1, it requires the carrier 0.5 seconds of for amplitude, and followed by 0.5 seconds reduced amplitude. Other radio clock signals like WWB, DCF-77 also can be implemented with this way. I get this ferrite loop stick antenna from my GGY receiver module. In fact, this antenna is used as an inductor while connected with the proper capacitor in parallel. It can be used to transmit the 60 kHz carrier. When we want to transmit the 77.5 kHz carrier, just change to another capacitor. This is the whole circuit of the uniform transmitter. We don't use any amplifier here. It's very simple. You also can play with it. If you want to transmit over long distance, just 8-dipole amplifier and a big antenna. But be careful of breaking the law. Now the tool to hack a radio clock is prepared. And let Haoqi show you how to forge GPS signal.
Hi. Okay. Can you hear me? Oh. Thanks to you is introduced to the JDY bird, and apologize to our accent. And let me introduce how to attack an GPS NTP receiver. So as you can see, NTP server's clock reference is not just a JDY bird or something else, and mostly we will use the GPS NTP GPS signal receiver. So we will introduce the GPS time spoofing tech in these ways and in detail. So firstly, we will talk about the most common GPS receivers that we will use and we can buy in China. And in order to make you guys understand what's the meaning of the source code we just write, and we will briefly introduce the GPS text principle. And I will generate a real GPS signal to spoof our GPS receiver bird that we just bought and gonna have a try. And but in this attempt, we will still have some shortcomings in it, and you cannot ignore them. So we're going to introduce how to upgrade our GPS signal generating algorithm. So let's start it. And so here is the GPS receiver that we can buy in China's market, and actually it's the most common GPS module that we can buy. So it got multiply connection, or you can say the interface. We can fetch the real time from 3 ways, such as PCIe and USB or serial port. So in our situation, and we will use this port we will use the serial port to get time from this. And so after the GPS NTP receiver bird, and we now to briefly introduce the GPS tag. So I don't know how many you guys know the detail of the GPS tag, but let me tell you, it's the principle is really complicated. So unfortunately, but it doesn't matter, because I don't know whether you guys listened to the presentation of this trick yesterday, and my colleague Dr. Huang, and just made a presentation about the LTE downgrade. So, she's the one who used to give presentation about how to make a GPS spoof signal last year in DEFCON 23. And so if you guys are really interested in the GPS spoofing details, I suggest you go to the YouTube and take the video. So here is the thing. And let's get back to something serious. And here's the 2 pictures. And the key information in these pictures is now we got a GPS receiver on the ground, and in the sky there is a lot of there is a lot of machines that can send the signals to the GPS receiver. And what we now to do is just to generate a bunch of signals in some real format, and we can make the GPS receiver think, wow, now here is where I am and what time I'm in, and so the important thing is how we generate this signal or you can say the wave. So in the second picture, here is the format of the GPS signal wave. And there is 5 subframe, and the important thing that in the subframe 2 and subframe 3, there is the information that can tell the GPS receiver where I am, and in the front of each subframe, and there is some information that can tell the GPS receiver now what time it is. So the location doesn't matter, but the time is important. And now we can, here is the main algorithm that we use to generate the GPS signal. So firstly, we need to get the information, the data, and there are 2 methods. One to download from NASA's website, and you can record it, but and I don't mean yeah, it's recorded, and so after that you can use the open source program or GNSS SDR to receive the real-time GPS signal and record it and get the fresh data. And so after you get this data, now you need to do is set the current time and the current location and the current height that the signal you want to generate. And so maybe you guys is wondering what are these things meaning, but it doesn't matter. It's open source and it's on GitHub. And if you guys are really interested, so you can download it and see and see which parameters is what's the real meaning of it. So let's gonna have a try. After we run this program, and we will generate a signal that conclude the time and the attitude that we want, and we put it in SDR, or you can say USRP, and we will generate the real GPS signal. So after we run it, and the picture higher is if you guys download the PDF of it, and you can zoom it, and you can see this is the real time. This is exactly the time that we just generate in our recent code, and so here is the result. The NT server is panicked, and as you can see in this third line, and it's negative 4,000. It's 4,000 seconds ahead. So why it's panicked? We will introduce later, but we'll introduce later, and but we will have something more something related to introduce. Is how to update, or you can say upgrade the attack algorithm. Because if you guys really run this MATLAB code that we just use, you will find out that if you want to generate a GPS signal, it costs so many times, about 20 minutes, and we need a lot of storage space, such as about 4 gigabits, and it's not real time. If you want to attack one NTP server, and you now to use a laptop, and cost 20 minutes, and got not exactly the time that you want. So we need to update it. So in the GPS generated algorithm source code, we will find out where is the GPS time that we use. And so what we need to do is generate a GPS signal and find out where is the GPS time binary code is, and replace it and recheck the parity. So the principle is really easy, and what we need to do is just write a Python program and read the data file and rewrite it, and we put it in the USRP and we play it, and that's all fine. So after we introduce the NTP server and the detail of the detail tech of the JDY bird and the GPS receiver, and let's try to attack a real one NTP server. So let's just make some prototype and try to use it. So what we now to do is to set up an NTP server. And here is the detail. Over here is the key point of the NTP server's config file. Yeah. And here is the JDY. Here we set up it as a JDY bird and as its clock reference. And here is the screenshot. And now we just set the NTP server's IP address to the NTP server that we just set up. So when we use the Wireshark to capture the network traffic, as you can see, in the reference ID is JDY. So that means our NTP server is now working. So let's can attack it. So as we just introduced, now we need to do is control our JDY bird and send to the data and try to make it to send out the signals and to influence the NTP server. So, but the thing is that matters is, can we inject any time? Remember, we just generate a GPS signal, and we give him a time that ahead about 4,000 seconds. But the thing is, the NTP server is just crashed. So here is the thing: the NTP server, if you read the source code, and we will notice that if the time that the NTP server just get from its reference clock, and the distance is really big, so the NTP server will crash and will panic, and it's the limit. So what we need to do is just the largest jitter limits that we read the source code and we excise, and we find out it's 4 hours. And that means if you inject a time that is ahead or behind the time that the NTP server really is, and it's larger than the 4 hours, and it will panic. So what we need to do is just to short the distance. So it's not what we want, and it's not whatever we want. So, but after we tried to inject 1 hour that behind, or you can say slower than a real time, but after that the NTP server just close it, just lost its connection. So why it is? That means actually there is a lot of more limits in there. And we try to find out, and we find out the time offset is more than 1,000 times, so the server will shut down. it's not just 4 hours, and and the 4 hours is the first step, first limit. Then the next limit is 1,000 times, 1,000 seconds. That's the NTP implementation. It's really close. And so now what we can do is just to make things slower, because if you want to inject any time, what we need to do is try to that is the first time we inject a time that the offset is not more than the 1,000 seconds, and such as we use the 900 seconds, and after this step effected, and we will inject another 900 seconds. So that's more and more and more and more, and this is quite slow. And there is a little bit more shortcomings. That is the root dispersion. And if you tried this, if you want to try this this exercise, there is a lot of more limits in there, because when we just to capture the network traffic, there is a root dispersion in it. That is actually not a limit to the server, it's a limit to the client. The client will just to calculate the difference between the local time to the network time. So when this distance is too large, and the client will just close its connection. So here is another limit. So if you want to what we solve this problem is just to make it more slower, and in our attack script, and we consider about the kernel, the NTP server panic, and the client closes connection, and so after this, our access will make effect. So if you guys want more details, the request for comment 5905, it's just met this limit. And if you want to know about more details, you can just read it. So here's our attack demo that we just record. So I want it. So as you can see, this phone that is used, we set up its NTP server's IP address to the server that we just set up, and this clock, it means real time, and it's not quite clear. But if you see more closer, and you can see the numbers we just typed on the behind. That means we just what we do is now we try to control the JJY bird and make it to influence our NTP server. That is. So if you can see in it, and it's this time that we use is about 4 o'clock. That we in the afternoon. Sorry. Where's my mouse? So here is the influence that the real time is about 2 o'clock, and the influence time is about 3 o'clock and a half, and now we try to manage it's about 4 o'clock. So here is this is the difference, and this is difficult things that if we want to make things, we want to change the NTP server, and it will cost so many times. And we just made this distance about 1 hour, and we just use about 30 minutes to make it come true. So what I just introduced is just a prototype that I set up. But in real time, maybe you guys want to ask why not just buy a real NTP server and just attack it and record a demo. So here is the thing. This NTP server is just so expensive, about $10,000 and each machine. So if you guys know about some guys in this NTP server NTP server company, and you can tell them we are glad to offer the tech details and tell them how to retest their NTP server. So there is a lot of NTP servers company that made this, and as you can see, we got the as you can see, we got the I'm sorry. Yeah, Marienburg is a large company that made NTP server, and such as more products and here is the Think server and the S200, and all these tools come from the foreign company, and the three is more. Solomon is another. And here is the NTP server in China that we made. And when we made conversations with them, and we know a lot about things about where they use this, where they use the NTP server, and how many people will really buy this NTP server, and where they want to put it and where they use it. And after we made this conversation, and we know a lot about actually in China, there is in prison and police station and bank and electronic system, they use such as these models. And according to our tech, our spoofing tech, and their engineer told us that seriously, their products cannot prevent from this time spoofing. So maybe we come close to this place, such as prison, such as bank, and we made this attack. So this system will just crash. And after we Googled it, and here is another real attack, maybe an example. That we just know it's about one guy. And last year they just posted an article about their bank NTP server, and told us their NTP server, they don't know why they just crashed, and this bank only use this one NTP server as the root NTP server. So after it crashed, their engineer has to update the time manually, and it's almost a disaster. So here is our reference, and our most thankful the author is it's my colleague and Dr. Huang, and made GPS spoofing, and she made us work more easier than usual. And the GGY bird and the DCF 77, and so that's okay. That is the end of our presentation. Thank you. So Do you guys got any problem? Any question? Thank you. Nope.
Okay, does anybody have any questions?
Yeah. So you got further more questions? We have the first page is our email address, so feel free to contact with us.
No questions? Okay, thanks a lot for the talk.
Thank you.
It was fun.